3 days ago, a PDF surfaced on an encrypted forum. It contained 37 pages of Hubble data. On page 19, there was red text indicating a secondary signature was detected. A warning followed, "Do not distribute." Just 6 hours later, the file was gone. Servers wiped, but 1847 individuals had already downloaded it. What those pages reveal about an object accompanying Comet 3, I-Atlas, has scientists questioning their silence. Amateur astronomers are trading theories. And one Harvard physicist wonders, what if this isn't a comet? We're digging deeper into areas NASA won't go. If you're intrigued, like and subscribe, only if you're genuinely invested. Drop a comment with where you're from and when you're listening. I read them all. Share this with someone who needs to hear it. Now, turn off the lights, settle in, and let's uncover what they tried to conceal. The file appeared at 2:47 a.m. Eastern Time on October 18th, 2025. You know this precise timestamp because the metadata was still embedded in the PDF when it first appeared. Someone at NASA's Jet Propulsion Laboratory either made a mistake or wanted to be found. Either way, within minutes, a small part of the internet most people are unaware of went into a frenzy. The forum it appeared on isn't your typical Reddit or Facebook thread. It's an encrypted message board frequented by amateur astronomers, retired aerospace engineers, and people who track satellites for fun. The post was simple. No dramatic message, just a download link and 3 words. Look at page 19. By 3:15 a.m., 17 people had opened the file. By dawn, 1847 people had downloaded it. Then, as suddenly as it appeared, everything vanished. The original post was deleted, the user account disappeared, and the backup server in Iceland hosting the PDF was wiped clean. But here's the thing about the internet. Once something is out there, it can't truly be erased. So what was in those 37 pages that made someone risk their career, possibly their freedom, to get it into public hands? The document opens with standard Hubble Space Telescope observation logs. If you've never seen raw space data, imagine an Excel spreadsheet from 1997 mixed with the world's most boring spreadsheet. It's filled with columns of numbers, timestamps, and wavelength measurements. This data is usually processed by software first, then reviewed by graduate students working late nights fueled by caffeine and the faint hope of tenure. But page 19 is where everything changes. Have you ever been reading something perfectly normal and then encountered a sentence that makes you stop and reread it 3 times? That's what happened to those first 17 people. In the middle of routine observations of Comet 3, I-Atlas, between March 8th and March 22nd, 2020, a strange notation appeared. It was in a different font. The rest of the document was formatted using the standard NASA Courier News, but this note was Times New Roman, bold, 14-point red text, standing out like it didn't belong. It read, "Secondary signature detected at 0.31 arcsec, offset. Magnitude variance suggests non-tri-albedo flagged for ITAR review. Do not distribute." Let me break that down. Someone at Hubble, while photographing a comet, caught something else in the frame. This object was close enough to the comet to be travelling with it, but different enough that it didn't look like a typical chunk of ice and rock. And then someone classified it under ITAR, International Traffic in Arms Regulations, the US law controlling information about space and defense technology. Why would you classify a comet observation under weapons regulations? Now, 0.31 arcseconds might sound small, and it is, but we're talking about an angular separation roughly equal to spotting a dime from 2 meters away. In space terms, at the distance Comet 3I Atlas was from Earth in March 2020, that corresponds to about 5,000 kilometers actual separation. For context, the International Space Station orbits at about 400 kilometers above Earth. This object, whatever it was travelling alongside the comet, farther away than the Earth's entire circumference. The leaked data includes 4 separate observation sessions, March 8th, 11th, 18th, and 22nd. Each time Hubble's Wide-Field Camera 3 pointed at Atlas, the secondary signature appeared. Same position, same unexplained brightness. Here's where it gets interesting. Between March 18th and March 22nd, the comet began to fragment. Comet fragmentation is common when they pass too close to the sun. The ice sublimates. internal pressure builds and the comet shatters. But the secondary object, it remained in the same position, same trajectory, moving through the debris field as if it was following a preset path while everything else fell apart. Imagine you're watching two cars driving side by side. One hits a massive pothole, explodes and shatters across 3 lanes. The other car keeps going, unscathed, at the same speed, in the same lane. You'd probably have some questions about that second car, right? The document also includes spectroscopic data, which provides a fingerprint of an object based on the way it reflects light. Atlas's nucleus showed typical water ice, rocky silicates, and organic compounds, standard comet material. But the companion object? Its spectroscopy didn't match. Its albedo, reflectivity, came in at around 0.12, while Atlas's nucleus was at about 0.04. This object was 3 times more reflective than the comet it was travelling with. Handwritten notes in the margins of the document were included, not digital annotations, actual pen-on-paper notes, which were then scanned. This tells us the document existed as a physical printout before it was digitized. One note next to the spectroscopy data says, checked calibration 6x, not instrument error, not ghost image, real. Another note on page 23 reads, if not natural, what clearance level decides when the public has the right to know? And that's the question, isn't it? At what point does scientific discovery become classified information? NASA's official stance on leaks is straightforward. They don't comment on unverified material from unknown sources. But within 48 hours of the PDF's release, something curious happened. The Hubble Space Telescope's observation schedule, which is publicly available and updated weekly, showed a sudden gap. 6 hours of scheduled observations on October 21st disappeared, replaced with a note for instrument maintenance. What an odd coincidence, right? Here's what we know for sure. The observation data is real. Multiple amateur astronomers have verified the timestamps and positional data against the known location of 3I Atlas during March 2020. And it checks out. This isn't some hoax. The data came from within NASA. What we don't know is why it was kept hidden for 5 years. Atlas broke apart in April 2020, and by May, it was just a fading cloud of ice. Papers were published, data archived, and everyone moved on. Except, apparently, the person who wrote those margin notes. But before we judge whether NASA was right to keep this quiet, we need to understand what 3 Atlas actually was. Because here's the kicker. It wasn't even a true interstellar object. Not technically. And that's where the story takes an even stranger turn. Let's clear up a misunderstanding. The name 3 Atlas is intentionally misleading. That I stands for interstellar. Technically speaking, this comet wasn't interstellar at all. Your mind might immediately jump to Oumuamua, that cigar-shaped anomaly that streaked through our solar system in 2018, sparking countless conspiracy theories. Or perhaps to 2I Borisov, the confirmed interstellar comet discovered in 2019 by a Crimean amateur astronomer with a homemade telescope. These objects came from beyond our solar system, travelling through the space between stars for millions of years, just passing through our cosmic neighbourhood on their way to somewhere else. Comet 3I Atlas? It's a different story. Comet 3I Atlas was discovered on December 28, 2019, by the Atlas Survey System in Hawaii. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to spot objects that could impact Earth before they do. That night, the automated system flagged a faint smudge against the background stars with a magnitude of 19.6, meaning you needed a decent telescope to see it. Initially, no one was excited. Comets are discovered all the time, and the Minor Planet Center catalogues dozens each year. But as more observations came in and astronomers started calculating its orbit, something unusual appeared. The trajectory showed an eccentricity of 0.99999, meaning the comet was barely bound by the sun's gravity. One small nudge, and it would be gone forever. It also had an inclination of nearly 45 degrees to the plane of the solar system, coming in from above the ecliptic, where most comets reside. Its perihelion, the closest point to the sun, was going to be just 0.25 astronomical units. For reference, Mercury orbits at 0.39 AU. This comet would get closer to the sun than the innermost planet in our solar system. Dr. Kwanzi, from the University of Maryland, one of the first professional astronomers to analyze Atlas, said in a January 2020 paper, "The orbital elements suggest a dynamically new comet, possibly from the Oort cloud, making its first passage through the inner solar system." In other words, this comet had been frozen at the edge of our solar system for 4.5 billion years, until something kicked it inward, perhaps a passing star's gravity, or a collision with another icy body. We'll probably never know. But here's where excitement really began to build. As Atlas approached the Sun in February and March 2020, it brightened rapidly, faster than expected. By mid-March, it had jumped from magnitude 19 to magnitude 8, visible with binoculars. Projections suggested that by late May 2020, as it passed closest to the Sun, Atlas could reach magnitude 10, making it brighter than Venus and visible during the day. The kind of comet people would remember forever. Social media exploded. Astronomers posted updates daily. News outlets ran stories about the Great Comet of 2220, arriving just as the pandemic lockdowns left everyone searching for beauty in the skies. But then in early April, Atlas started to fall apart. The first sign came on April 5th, when the comet's brightness suddenly dropped. This wasn't the gradual dimming you'd expect due to changing distance, but a sharp, sudden fade. Within days, telescopes revealed the nucleus had fragmented into at least 4 distinct pieces. By April 11th, amateur images showed the comet as an elongated smudge, rather than a single point of light. Fragmentation isn't unusual for comets. It happens. Comet Shoemaker-Levy 9 broke into 22 pieces before colliding with Jupiter in 1994, giving us one of the most spectacular astronomical events in modern history. Comet Linear disintegrated in 2000. Comet Ison, which everyone thought would be the comet of the century in 2013, evaporated as it passed the Sun. But when a comet fragments, we can usually track the pieces. They follow predictable paths, and we can measure their brightness as they continue to break down or sublimate away. That wasn't the case with Atlas. Initial observations from professional telescopes at Gemini North in Hawaii confirmed 4 major fragments, labelled A, B, C, and D. Fragment A was the brightest, probably containing around 40% of the original nucleus. The others were smaller, trailing behind in a line like ducklings following their mother. This was what you'd expect from a comet with structural weaknesses that couldn't handle the thermal stress of approaching the Sun. But then things got strange. By late April, only fragments A and B were still visible. C and D had faded beyond detection. The standard explanation was that they'd completely disintegrated into gas and dust, as small fragments tend to do. But then, on April 23rd, amateur astronomer Carlos Ferrer in Chile, using a 14-inch Schmidt-Cassegrain telescope and a modified DSLR camera, captured something that didn't fit. His images showed fragments A and B exactly where they should be. But there was also a 5th point of light moving through the expanding debris field at an angle that didn't match the expected trajectory of any fragment. Ferrer posted his images on astronomy forums with a simple question. Anyone else seeing this? Within hours, 3 other amateur astronomers confirmed similar observations, an object roughly magnitude 14, travelling at a velocity that suggested it wasn't following the same orbital path as the confirmed fragments. Professional telescopes didn't pick it up, or if they did, they didn't publish the data. Official catalogues continued to list only 4 fragments, with C and D marked as disintegrated by early May. By June 2020, even fragments A and B had faded below naked eye visibility, and scientific interest in Atlas dropped off sharply. The Great Comet of 2020 became a footnote in astronomy history, mostly remembered for its anticlimactic end during a year that was already full of disappointments. But Carlos Ferrer's images stayed online. And now, 5 years later, in light of what the leaked Hubble data reveals, people are going back to those April observations with fresh eyes. If there was a companion object travelling alongside Atlas before it fragmented, and if the object survived the breakup while the comet itself disintegrated, what exactly were the amateur astronomers photographing in late April? Was it fragment D somehow surviving longer than expected? Or was it something else entirely, something hidden within the comet's brightness, only revealed when the nucleus shattered, uncovering what had been flying alongside it all along? Now let's talk about what the leaked Hubble data reveals, because this is where things shift from a fascinating scientific puzzle to a situation where something isn't quite adding up. To understand what the data shows, you need to know how space telescope observations work. When Hubble takes a shot, it's not like snapping a picture with your phone. The Wide Field Camera 3 captures light across multiple wavelengths simultaneously, building up exposure over time to catch incredibly faint objects. Each observation session generates gigabytes of raw data, processed through multiple calibration steps before anyone even reviews it. The leaked document shows 4 separate observation windows: March 8th, 11th, 18th, and 22nd, 2020. Each session lasted between 42 and 96 minutes, with multiple exposures stacked to improve the signal-to-noise ratio. Standard procedure for observing a comet that's still far from Earth and faint enough that you need to collect every photon possible. The March 8th observation shows Atlas as expected, a slightly fuzzy point source with a developing coma, the cloud of gas and dust surrounding a comet's nucleus as it warms up near the Sun. The brightness measurements match ground-based observations from that same period, around magnitude 8.5. Everything looks normal. But then at exactly 0.31 arcseconds offset from the nucleus, consistently across all 12 exposures taken that night, there's a second point source, a fainter object, roughly magnitude. At magnitude 13.2, the object was definitely there. It wasn't a cosmic ray hit, because those appear as single pixel streaks in one exposure and vanish in the next. It wasn't a background star either, because it moved with Atlas between exposures. Nor was it a ghost image or an internal reflection in the optics, as the brightness and position didn't match the patterns those artifacts typically create. The official analysis, written in standard NASA technical language, classified it as potential fragment or satellite debris. This seemed like a reasonable first assumption. Comets can have small chunks near them, fragments from previous passes, or impacts with meteoroids. But then look at March 11, just 3 days later. Atlas had moved significantly along its orbit, yet the companion object was still there, still at 0.31 arcseconds, still at magnitude 13.2. If this was a fragment or debris, orbital mechanics says it should have drifted. Space isn't sticky. Objects don't just stay together unless they're gravitationally bound. And Atlas was far too small to hold anything in orbit, at a distance of 5,000 kilometers. Now, March 18th is where the spectroscopic data gets really interesting. Hubble's instruments break down the light from an object into its component wavelengths, revealing its composition. It's like a chemical fingerprint. Different materials absorb and reflect different colours of light in characteristic patterns. Atlas's spectrum showed the classic signatures of a comet nucleus, strong absorption lines indicating water ice, along with carbon dioxide, carbon monoxide, and various organic compounds. When sunlight heats these materials, they sublimate directly from solid to gas, creating the coma and tail that make comets so beautiful. The reflectivity spectrum matched what you'd expect from a dirty snowball, the standard model for comet composition since Fred Whipple proposed it in 1950. But the companion object's spectrum was completely different. First, the albedo. Atlas reflected about 4% of the light hitting it, typical for a carbon ice-coated surface. The companion reflected 12%, 3 times more reflective. You see that kind of albedo in metallic asteroids, objects with exposed silicate rock, or icy surfaces that are extremely smooth and clean. But here's the problem. If it was metallic or rocky, we'd see specific absorption features in the spectrum, like iron, nickel, or silicon compounds. Those features aren't there. If it was clean ice, we'd see the water ice signature, also absent. The spectrum was nearly flat across the visible and near-infrared range. That's called a neutral spectrum, and it's rare. Most natural objects in the solar system have distinctive spectral slopes or features based on their composition. The leaked document includes a handwritten note next to the spectroscopy plot. Compared to 312 known NEO spectra, no match. Compared to 89 comet nuclei spectra, no match. Compared to catalogue of spacecraft and debris, no match. Someone did their homework. They went through every possible comparison they could think of and came up empty. March 22nd's observation is the most revealing, because this is when Atlas was clearly starting to fragment. The nucleus had elongated, stretched by tidal forces and internal stress, as volatile ices heated up and created pressure. Professional telescopes would confirm visible fragmentation within 2 weeks, but Hubble caught it early. The images from March 22nd show Atlas's nucleus as distinctly non-spherical, already breaking into what would become the 4 major fragments. The coma had brightened and expanded as fresh ice was exposed to sunlight. Essentially, the comet was falling apart at the seams, yet the companion object was still there, still maintaining the same separation, still the same brightness, still showing that flat, featureless spectrum. Now here's what stands out in the data. Between March 8 and March 2010, Atlas moved about 0.43 astronomical units along its orbit. That's roughly 64 million kilometers. During the same period, the companion object maintained its relative position to within the measurement precision of the telescope, which was about 0.02 arcseconds. Do you know how precise that is? It maintained a formation spacing of 5,000 kilometers, while both objects travelled 64 million kilometers through space, threading through the gravitational influences of the Sun, Earth, Venus, Mars, and Jupiter. That's like 2 airplanes flying side by side from New York to Los Angeles, while staying within 10 feet of each other the entire way, with no radio communication or coordination. Natural objects don't do that. Even binary asteroids, where 2 rocks orbit their common centre of mass, show measurable variation in separation distance as they move. Gravitational perturbations from planets, solar radiation pressure, and outgassing from the comet would all cause drift. The leaked data also includes orbital element calculations for both objects. Atlas had an eccentricity of 0.999142, with specific values for its semi-major axis, inclination, and argument of perihelion. These are standard orbital mechanics parameters. You can plug these numbers into any astronomy software and predict exactly where Atlas should be at any given time. The companion object's calculated orbital elements are nearly identical, matching to 5 decimal places in some parameters. That's not approximately the same orbit. That's precision formation, flying. The last page of the leaked document has a note that wasn't scanned properly. The text is partially cut off, but you can make out the phrase, "Trajectory analysis suggests active station keeping. No known natural mechanism can explain maintenance of relative position across observed time period. Recommend escalation to..." And that's where the page cuts off. Station keeping is a term from spacecraft operations. It means actively adjusting your trajectory to stay in a specific position relative to something else. Satellites do it. The International Space Station does it. Comets don't. So we're left with a question that has exactly 2 possible answers. Either the laws of orbital mechanics, as we've understood them for the past 400 years since Kepler, are wrong, or something was actively controlling its position next to that comet, and honestly, I'm not sure which answer is more unsettling. Before we dive any deeper into this rabbit hole, we need to stop and ask ourselves an uncomfortable question. Are we seeing what we think we're seeing? Or are we doing what humans have always done, finding patterns in noise and mistaking the unknown for the impossible? Because here's the thing about space mysteries. We've been wrong before. A lot. Let me take you back to September 20th, 1976. The Soviet Venera spacecraft orbiting Venus captured an image that caused a minor panic in certain circles. There, in the photograph, clear as day, was a bright reflection that didn't match anything in the instrument's field of view. It appeared elongated, metallic-looking, and seemed to be moving independently of Venus's cloud formations. For about 3 weeks, a small group of researchers quietly speculated about what it was. Some suggested it was an unknown atmospheric phenomenon. Others proposed it was debris from a previous mission. The more imaginative minds whispered about something else entirely, something that might be observing our probe, the same way we were observing Venus. The truth? Lens flare, a specific type of internal reflection caused by Venus's incredibly bright cloud tops, overwhelming the camera's dynamic range. Once engineers understood the geometry of the optics and lighting conditions, they could reproduce the artifact perfectly in testing. Mystery solved. Lesson learned about jumping to conclusions. Or how about October 19th, 2017? Pan-STARRS-1, a telescope in Hawaii, detected something that changed everything. Object 1I 2017 U1 later named Oumuamua, which means scout in Hawaiian. This object was strange from the start. Its orbit showed it definitely wasn't from our solar system. But the shape? Elongated, somewhere between a 5.1 and 10:1 length to width ratio, like a cigar, or exactly what you'd design if you wanted to build a spacecraft that could travel between stars efficiently. Then it got even weirder. Oumuamua accelerated slightly as it moved away from the Sun, just 0.1 ms2, but enough to deviate from predictions. For a comet, that's normal, outgassing creating a tiny rocket effect. But Oumuamua showed no coma, no tail. There were no signs of any outgassing whatsoever. Harvard physicist Avi Loeb published a paper suggesting that we should seriously consider the possibility that Oumuamua was artificial, perhaps a light sail propelled by starlight. The scientific community mostly dismissed the idea. The consensus settled on it being a weird comet with an unusual composition. But the point is, we still don't actually know. Oumuamua is now gone, travelling into deep space, and we'll never get another chance to observe it. Maybe it was a natural object and we just don't understand all the ways comets can behave. Or maybe Loeb was right. The universe doesn't care about our consensus opinions. Then there's my personal favourite, 2020 ESO, discovered in September 2020. This object had an orbit suspiciously similar to Earth's. Its spectrum didn't match any known asteroid type. Its trajectory showed tiny accelerations. Speculation ran wild. Was this a captured asteroid, something monitoring our planet? NASA tracked it carefully, and in December 2020 they announced what it actually was: the Centaur Upper Stage from the Surveyor 2 mission, launched in 1966. It had been floating around in solar orbit for 54 years, before Earth's gravity temporarily captured it again. We had literally been observing a piece of 1960s American rocket hardware, and we didn't even recognize it. These examples are important because they establish a pattern. Most of the time, when we see something we don't understand in space, it turns out to have a natural explanation. The universe is strange enough without needing to invoke anything extraordinary. So, what are the most common mistakes people make when analysing unusual observations? The first is confirmation bias. Once you decide you're looking at something anomalous, your brain starts filtering data to support that conclusion. You focus on every detail that seems unusual and unconsciously dismiss the details that suggest normal behaviour. Scientists are just as susceptible to this as anyone else. The second is resolution limits. Hubble is incredible, but it's not magic. At the distances we're talking about, objects smaller than a few kilometres might appear as single pixels. That means we're trying to extract information from extremely limited data. It's like trying to identify someone's face in a photograph, where their entire head is only 4 pixels. You might convince yourself you see specific features, but you're mostly seeing what you expect to see. Third is misunderstanding orbital mechanics. Space doesn't work like Earth. Objects don't need engines to maintain orbits. They don't slow down from friction. Weird trajectories that seem impossible often turn out to be perfectly normal, once you account for all gravitational influences and actually do the math properly. I've seen people claim objects are violating physics because they don't understand how solar radiation pressure affects small particles, or because they forget that planets are constantly moving and their gravitational influences change. Orbital mechanics is genuinely difficult. There's a reason aerospace engineers spend years studying it. Now, applying all that skepticism to the Atlas companion object, what natural explanations should we eliminate first? Binary comet systems exist. The 67P Churyumov-Gerasimenko comet that the Rosetta mission visited turned out to be 2 distinct lobes stuck together. If Atlas had a chunk gravitationally bound to it, that could explain a companion. But the separation distance doesn't work. Atlas's nucleus was probably 5 to 10 kilometers across, with a mass around 1 trillion kili at most. To hold an object in orbit at 5,000 kilometer distance, you'd need far more mass. The math doesn't close, so binary comet is ruled out. What about a Trojan configuration? Earth has Trojan asteroids at its L4 and L5 Lagrange points. Could Atlas have temporarily captured something there? It's theoretically possible, but those points are only stable with a significant mass ratio like Earth and the Sun. A tiny comet like Atlas doesn't create stable Lagrange points that could trap anything for more than a few weeks. We observed the companion for at least 14 days across different orbital positions. Trojan configuration is ruled out. What about debris from an ancient collision? Maybe Atlas collided with something years ago, creating fragments in similar orbits. We see this with asteroid families where hundreds of smaller rocks share nearly identical orbits because they came from the same shattered parent body. But spectroscopy kills this idea. Atlas showed typical comet composition, while the companion showed that weird neutral spectrum with a higher albedo. If they came from the same parent body, they should have the same composition. You don't get metallic-looking fragments from an icy comet collision. The idea of collision debris doesn't fit either. This is actually the most reasonable natural explanation, and it's probably what most astronomers would default to, except the leaked data includes those handwritten notes about checking calibration 6 times and comparing against known artifact patterns. Whoever analysed this data knew what ghost images look like and explicitly ruled those out. Plus, if Hubble created a ghost image at 0.31 arc-seconds offset under certain conditions, it should do that every time. But other comet observations from the same period using the same instrument don't show these secondary signatures, just Atlas. And that brings us back to the uncomfortable conclusion. If we've eliminated the natural explanations and accounted for observational errors and instrumental quirks, then we're left with something unprecedented. That doesn't automatically mean it's artificial. It doesn't mean aliens. It means we're looking at a phenomenon we don't yet understand, and that's actually the most exciting place to be in science. That's where discoveries happen. But it also means we need better data, more observations, different instruments, and that's where this story takes a frustrating turn. Because the one thing we need most is the one thing we're not getting. Transparency from the people who have access to the information. All right, let's do something that might seem counterintuitive. Let's actively try to prove ourselves wrong. Let's take every possible natural explanation for the Atlas companion and push it to its absolute limits. Because if there's one thing science has taught us, it's that nature is far more creative than we give it credit for. Start with the most basic question. What holds things together in space? Gravity, right? It's the weakest of the 4 fundamental forces, but over large distances, it's the only one that matters. For 2 objects to orbit each other, you need enough gravitational attraction to overcome their tendency to just fly off in straight lines. But with a comet, we're talking about a dirty snowball, maybe 10 kilometers across. Let me put that in perspective. If you scaled Earth down to the size of a basketball, Atlas would be smaller than a grain of sand. I actually did the math using Newton's law of universal gravitation. If Atlas had a mass of about 10 trillion kg, which is generous, and the companion had a mass of maybe 1 million kg, the gravitational force between them at 5,000 kilometer separation would be about 0.04 newtons. That's roughly the force you'd feel if a mosquito landed on your hand, except in space, between 2 objects each travelling at tens of kilometres per second. That force is nowhere near strong enough to keep 2 objects in stable formation for 2 weeks, let alone through the violent fragmentation that tore Atlas apart. So, gravitational binding's off the table. What about electromagnetic forces? Comets can develop substantial electric charges as they interact with the solar wind. When charged particles from the sun hit the comet's coma, they can create charge separation, building up voltage differences. But to hold 2 objects in formation electromagnetically, you'd need them to have opposite charges and be close enough that the force overcomes the sun's gravity, trying to separate them. There were no signs of any outgassing whatsoever. Harvard physicist Avi Loeb published a paper suggesting that we should seriously consider the possibility that Oumuamua was artificial, perhaps a light sail powered by starlight. The scientific community largely dismissed this idea. The consensus was that it was simply a strange comet with an unusual composition. But the truth is, we still don't really know. Oumuamua has moved on, travelling deeper into space, and we won't get another chance to study it. Perhaps it was a natural object and we just don't fully understand how comets can behave. Or maybe Loeb was right. The universe doesn't care about our consensus opinions. Then there's my personal favourite, 2020 SO, discovered in September 2020. This object had an orbit strikingly similar to Earth's. Its spectrum didn't match any known asteroid type, and its trajectory showed tiny accelerations. Speculation ran wild. Could this be a captured asteroid? Something monitoring Earth? NASA tracked it carefully, and in December 2020, they revealed its true nature. The Centaur upper stage from the Surveyor 2 mission, launched in 1966. It had been drifting in solar orbit for 54 years before Earth's gravity briefly captured it again. We had been observing a piece of 1960s American rocket hardware, and we didn't even recognize it. These examples are important because they reveal a pattern. Most of the time, when we encounter something we don't understand in space, it turns out to have a natural explanation. The universe is strange enough without needing to invoke anything extraordinary. So, what are the most common mistakes we make when analysing unusual observations? The first is confirmation bias. Once you decide you're looking at something anomalous, your brain starts to filter data to support that conclusion. You focus on every detail that seems out of place, while unconsciously dismissing the details that suggest normal behaviour. Scientists are just as prone to this as anyone else. The second is resolution limits. Hubble is amazing, but it's not magical. At the distances we're dealing with, objects smaller than a few kilometres might appear as a single pixel. That means we're trying to draw conclusions from very limited data. Imagine trying to identify someone's face in a photo where their entire head is only 4 pixels. You might convince yourself you see features, but you're mostly seeing what you expect to see. The third is misunderstanding orbital mechanics. Space doesn't work like Earth. Objects don't need engines to stay in orbit. They don't slow down due to friction. Odd trajectories that seem impossible often turn out to be perfectly normal once you consider all gravitational influences and actually do the math. I've seen people claim objects are violating the laws of physics because they don't understand how solar radiation pressure affects small particles, or because they forget that planets are constantly moving and their gravitational pull changes. Orbital mechanics is difficult. There's a reason aerospace engineers spend years mastering it. Now, applying all that skepticism to the Atlas companion object, what natural explanations should we rule out first? Binary comet systems exist. For example, the 67P Churyumov-Gerasimenko comet, which the Rosetta mission visited, turned out to be 2 distinct lobes stuck together. If Atlas had a chunk gravitationally bound to it, that could explain the companion. But the separation distance doesn't add up. Atlas's nucleus was probably 5 to 10 kilometers across, with a mass around 1 trillion kilig at most. To hold an object in orbit 5,000 kilometers away, you'd need far more mass. The math doesn't work. So, binary comet is ruled out. What about a Trojan configuration? Earth has Trojan asteroids at its L4 and L5 Lagrange points. Could Atlas have temporarily captured something there? It's theoretically possible, but those points are only stable with a mass ratio similar to Earth and the Sun. A tiny comet like Atlas wouldn't create stable Lagrange points to trap anything for more than a few weeks. We observed the companion for at least 14 days across different orbital positions. Trojan configuration is ruled out. How about debris from an ancient collision? Perhaps Atlas collided with something years ago, creating fragments in similar orbits. We see this with asteroid families, where hundreds of smaller rocks share nearly identical orbits because they came from the same shattered parent body. But spectroscopy rules this out. Atlas showed typical comet composition, while the companion showed that strange neutral spectrum with a higher albedo. If they came from the same parent body, they should have the same composition. You don't get metallic-looking fragments from an icy comet collision. Collision debris doesn't fit either. This is the most plausible natural explanation, and probably what most astronomers would default to, except the leaked data includes handwritten notes confirming they checked the calibration 6 times and compared it against known artifact patterns. Whoever analysed the data knew what ghost images looked like and explicitly ruled them out. Plus, if Hubble created a ghost image at 0.31 arcseconds offset under certain conditions, it should show up every time. But other comet observations from the same period, using the same instrument, don't show these secondary signatures. Only Atlas. And that leads us back to the uncomfortable conclusion. If we've ruled out natural explanations and accounted for observational errors and instrument quirks, then we're left with something unprecedented. That doesn't necessarily mean it's artificial. It doesn't mean aliens. It means we're looking at something we don't fully understand, and that's actually the most exciting place to be. In science, that's where discoveries happen. But it also means we need better data, more observations, and different instruments. And that's where this story takes a frustrating turn, because the one thing we need most is the one thing we're not getting: transparency from those with access to the information. All right, let's do something that might seem counterintuitive. Let's actively try to prove ourselves wrong. Let's take every possible natural explanation for the Atlas Companion and push it to its absolute limits. Because if there's one thing science has taught us, it's that nature is far more creative than we give it credit for. Start with the most basic question: what holds things together in space? Gravity, right? It's the weakest of the four fundamental forces, but over large distances, it's the only one that matters. For two objects to orbit each other, you need enough gravitational attraction to overcome their tendency to fly off in straight lines. But with a comet, we're talking about a dirty snowball, maybe 10 kilometers across. Let me put that in perspective. If you scaled Earth down to the size of a basketball, Atlas would be smaller than a grain of sand. I actually did the math using Newton's law of universal gravitation. If Atlas had a mass of about 10 trillion kg, which is generous, and the Companion had a mass of about 1 million kg, the gravitational force between them, at 5,000 kilometer separation, would be around 0.04 newtons. That's roughly. Why the different approach when it comes to data concerning weapon systems and military technology? I reached out to 3 former NASA contractors who agreed to speak on background. This means I can share what they said, but not their names. These individuals worked in data analysis and mission planning during overlapping periods, and their accounts corroborate each other in interesting ways. Here's what one of them told me. When observational data doesn't match the expected model, there's a 3-tier review process. First, the science team examines it for possible instrumental errors or calibration issues. If they can't explain it that way, it goes to the program manager level. That's where decisions are made on whether the data is publishable science or requires additional review. Most anomalies get resolved at tiers 1 or 2, but occasionally something makes it to tier 3. This is when it crosses into policy. When releasing the data could impact national security, international relations, or public perception in ways that go beyond scientific curiosity, that's when other groups like the Department of Defense, DoD, or sometimes the intelligence community get involved. It's no longer just about the data, but about how releasing it might be perceived or used. Another former contractor put it more bluntly. Look, NASA is funded by Congress. Congress responds to public opinion and political pressure. If you're a program manager with data that could fuel conspiracy theories, get misinterpreted, or lead to congressional hearings questioning your budget, you'll be very careful about when and how that data becomes public. It's not conspiracy, it's bureaucratic self-preservation. But here's where it doesn't add up. NASA has dealt with odd data before without resorting to ITAR classification. The Mars face could have easily sparked conspiracy theories, but they released it anyway and dealt with the fallout. Oumuamua's unexplained acceleration could have caused wild speculation, but that data stayed public, and scientists openly debated it. So why was the Atlas Companion different? The timing offers a clue: March 2020. Do you remember what was happening that month? The COVID-19 pandemic was exploding worldwide. The World Health Organization declared it a pandemic on March 11th. By March 22nd, the date of the last Atlas observation, half the United States was under lockdown. NASA itself was transitioning to remote operations. The news cycle was dominated by infection rates, death tolls, and economic collapse. Maybe in that chaos, someone calculated that the anomalous data would raise questions they couldn't answer immediately. And maybe they decided that March 2020 was the worst possible time to add a mysterious object accompanying a comet to the list of public concerns. But once that decision was made, it became hard to reverse. When you classify something, when you create an official stance that certain data requires special handling, admitting you were wrong means admitting you suppressed scientific information for non-scientific reasons. This kind of decision-making has precedent. In 2021, the Pentagon released a report acknowledging 144 incidents of unidentified aerial phenomena observed by military personnel. They admitted they couldn't explain most of them, but the reports came after years of leaked videos and mounting public pressure. What changed? Not the data. It had been sitting in classified files for years. What changed was the political calculation. Someone decided that transparency, even when they couldn't explain the data, was less damaging than continued secrecy fueling speculation. The Atlas companion data might be stuck in that same calculation. In 2020, with the pandemic chaos, classification seemed prudent. Now, 5 years later, with leaks circulating and amateur astronomers asking questions, the classification starts to look like a cover-up, exactly the type of conspiracy theory NASA wanted to prevent. So we find ourselves in a situation where an agency that usually prioritizes transparency is now bound by its own earlier decision to suppress data. They can't release it without explaining why it was classified, and now that it's been leaked, they can't keep it classified either. It's not a conspiracy, it's a bureaucracy that made a questionable call under pressure, and now can't figure out how to undo it without making things worse. Which might be the most frustrating explanation of all, because it means we're not dealing with hidden truths. We're dealing with institutional paralysis. But while NASA sits frozen in its own procedural quicksand, the data exists. Data doesn't care about organizational politics. Numbers are numbers. Trajectories are trajectories. And independent analysts with the leaked documents are doing what NASA should have done 5 years ago, actually analysing the data. While NASA sat on classified data and bureaucrats argued about disclosure protocols, something interesting was happening on the corners of the internet where people actually know how to read orbital mechanics equations. Remember those 1847 downloads of the leaked PDF? Turns out a significant number of those people weren't conspiracy theorists or casual space enthusiasts. They were astronomers, physicists, and aerospace engineers who saw raw data and immediately thought, I can work with this. Within 72 hours of the leak, 3 independent analysis teams had formed, completely separate from each other, working in different countries. One group centered around retired JPL engineers in California, another at a university astronomy department in Germany, and the third was a loose collaboration of amateur astronomers and data scientists spread across 5 continents, coordinating through encrypted forums. All 3 groups reached essentially the same conclusions. This could either be an incredible coincidence or a sign that the data is telling us something real. Let's walk through what they found, starting with the most straightforward analysis, the albedo problem. Albedo is the fraction of sunlight an object reflects. Fresh snow has an albedo around 0.8 to 0.9, meaning it reflects 80 to 90% of incoming light. Charcoal, on the other hand, has an albedo around 0.04, absorbing most light and reflecting very little. Comet nuclei typically fall into the dark, carbonaceous range. They're basically dirty snowballs covered in dust, and organic compounds cooked by radiation over billions of years. The leaked Hubble data includes photometry measurements across multiple wavelengths, allowing albedo to be calculated. Atlas's nucleus had an albedo of 0.04, exactly what we'd expect. The companion object had an albedo of 0.12, 3 times more reflective. The German team ran the numbers through a comparative database of every spectral type catalogued in the solar system. Metallic asteroids, like 16 Psyche, can reach an albedo of 0.12, but they show distinctive absorption features from iron and nickel, which were absent in the companion spectrum. Icy moons like Europa have high albedos, but strong water ice signatures were also absent. What shows a neutral, featureless spectrum with a moderate albedo? Very few natural objects, and the ones that do are explained by specific surface processes that we can identify. One of the JPL engineers, I'll call him Richard, ran a contamination analysis. Could the companion's brightness and spectrum be explained by contamination from the comet's coma? When a comet is actively outgassing, the dust and gas around it can scatter light, creating false signatures. Richard's analysis showed that at 5,000 km separation, Atlas's coma would be too diffuse to significantly affect the measurements of a separate object. The companion's brightness and spectrum were its own, nothing to do with Atlas's coma. Then there's the thermal analysis. This is where things get interesting. When sunlight hits a comet, it heats up. The ices sublimate, turning from solid to gas. This process absorbs energy, cooling the nucleus. It also creates a detectable thermal signature. Infrared telescopes can measure this heat to determine composition, size, and activity level. Atlas showed exactly what you'd expect: a thermal signature consistent with water ice sublimation, with temperatures varying based on solar distance and rotation. The companion object, however, showed no thermal excess, no heat signature beyond what you'd expect from passive solar heating of inert material. Whatever this object was made of, it wasn't sublimating. It wasn't outgassing. It was just absorbing and re-radiating solar energy like a rock. This would be fine if it was a rocky asteroid, except its trajectory didn't match typical asteroid behavior. Objects in space follow trajectories determined by gravity. If you know an object's position and velocity, and you know the gravitational fields it's moving through, you can predict where it will be at any future time. This is called Keplerian orbital mechanics. It's been tested to absurd precision for over 400 years. The International Amateur Group ran the companion object's position data through multiple orbital determination software packages, SDK, GMAT, ORIT. They plugged in the March 8th position and velocity, then calculated where the objects should have been on March 11th, 18th and 22nd based purely on the Sun's gravity. The predicted positions didn't match the observed positions. The differences were small, just a few arc seconds, but they were consistent and directional. The companion was systematically offset from where pure gravitational dynamics said it should be. The direction of these offsets suggested a small but persistent acceleration in the direction tangent to its orbit. How small? About 0.03 ms2, that's roughly 3% of the acceleration you feel from gravity on Earth. Tiny, but over days it adds up. One member of the group, a doctoral student in astronomy, posted this comparison. Oumuamua showed a non-gravitational acceleration of about 0.01 and that caused a scientific controversy. This object showed an acceleration 3,000 times larger. Could it be measurement error? They checked. Hubble's positional accuracy for point sources is about 0.01 arc seconds. The offsets were larger than the error bars. Could it be software glitches? They used 3 independent programs and got the same results. Could it be that they didn't account for all gravitational influences? They included perturbations from every planet, major asteroids, and even relativistic corrections. But the gap didn't close. There's a term in astronomy for when your observed trajectory doesn't match your predicted trajectory residuals. These are the leftover differences after you've accounted for everything you understand. Small residuals are normal. They indicate measurement uncertainty. Large systematic residuals mean something significant is happening that your model doesn't include. The companion object had large systematic residuals, pointing in the direction of its motion, like something was pushing it forward along its orbit. Station keeping, the leaked note called it. The math backs that up. Richard from JPL put it most clearly in his public analysis. I know what natural trajectories look like. I know what thrusters look like. This looks like thrusters.